Welcome to Spring LIB.
Okay, so we're in chapter 35, problem 19 here. So we have two 0.01 millimeter wide slits that are separated by 0.03 millimeters. That's center to center. And it says, determine the spacing between interference fringes for 580 nanometer light on a screen 1 meter away. That's part A. Excuse me. So we should know that the double slit diffraction here gives this equation that sine of theta of the nth fringe is given by m lambda over d, the separation, and that the height of the nth fringe is given by L tan theta m. But this can be approximated for small angles as L m lambda over d. So for small angles now, we can say that delta y, which we can call y n plus 1 minus y n, is given as L n plus 1 lambda over d minus L m lambda over d. What this comes out to is L lambda over d. So we can just plug that in, and L is 1 meter. Lambda was 580 times 10 to the negative 9 meters, and our d is 0.03 times 10 to the negative 3 meters. So what we get out of this is 0.019 meters. And that is what our delta y is, which is exactly what we wanted, which was spacing between interference fringes. Sorry. Delta y is 1.9 centimeters. Okay, so what does part B ask? Part B says the distance between the two diffraction minima on either side of the central maximum of the envelope. Okay, so this is going to be the single slit diffraction of theta 1 is given by lambda over big D. And from this, we can just find theta 1 as the inverse sine of lambda over d, or inverse sine of 580 times 10 to the negative 9 meters over 0.01 times 10 to the negative 3 meters. And what we get here is a theta 1 of 3.325 degrees. So if this is our theta 1, this is from theta equals 0 to the first maximum, we can find the height of the first maximum, y1, and what we're trying to find is delta y, which is 2y1. Okay? So if we're trying to find 2y1, what does y1 equal? Well, this is L tan theta 1. So delta y is 2L tan theta 1, or 2 times 1 meter times tangent of 3.325 degrees. And we get a delta y here of roughly 0.116 meters. Cool.